Episode 2 created something powerful, a ball by ball match state dataset. But right now, it is just numbers. So in episode 3, we are going to answer the real question. From this exact ball, what's the probability of winning? And we are not doing it the shortcut way. We will build it properly by using train test split by match, real metrics, and plots. So, hi everyone, welcome back to the NIIT YouTube channel. So, this series is sport analytics where it meets real machine learning pipelines and not just theory, not just graphs, we build systems that you can reuse. So, quick recap of where we are. We already have the episode 2 pipeline done. That means we have a ball by ball.csv that lives inside the raw, and we also have two processed files, that is matchStateBall.csv and matchStateOver.csv. So episode 2 code, it generated us these two files, and this is under the processed. So we have a folder data, then under data we also have a folder processed, and then under processed we have these two CSV files. So except this, I have also created 4 sanity check plotins. So as you can see, we have our output plots. So you have 4 sanity check plots in, and those are their images over here. So episode 3, it starts after this. We are not touching raw ball by ball again. We are using the match state file as our training data set. So why episode 3 matters? In this episode, we will build a baseline win predictor. Baseline means it is simple enough to understand and strong enough to improve later. And our final goal is every ball in a chase has a probability between 0 and 1. Now, before I paste any code, I like to lock the scope using an anti-gravity prompt, because otherwise you end up writing random scripts that don't even connect to the previous episode. So I have my anti-gravity agent over here and I have this prompt. So what I'm going to do is I'm just going to paste this prompt over here. So I'll just go through the prompt so you have a better understanding. So our prompt is that we use Python with pandas, NumPy, matplotlib only. We have our input designated over here, and our task is to train a baseline win probability model for the second innings chases. And I have also laid out my requirements that are required. Then I have a split train test by match ID. I use features like runs remaining, balls remaining, wickets remaining, CRR, RRR, pressure, last 12 runs, last 12 wickets. Then we train a simple logistic regression using NumPy, and we save model to output models baseline log regression.json. Then we also have metrics report for outputs report and episode 3 metrics.txt. Then we generate plots, which can be an ROC curve, a calibration plot, coefficient bar chart, and one match win probability curve. At last, we print a small what if simulation result, and this prompt ensures that episode 3 produces the artifacts that we can reuse in episode 4, which is a model file, plots, and a report. So I'll just accept it again, and now I will let the anti-gravity to do its thing. So in episode 2, we built the matched state dataset for every ball in a chase. We now know the runs remaining, the balls remaining, the wickets remaining, the required run rate, everything. Now in episode 3, we do the fun part. We train a baseline model that converts match state into the win probability. So I'll also tell you the deliverable checklist that we require today and that we'll be covering today. So we load the match state ball from the episode 2. Then we split the train test by match ID so there's no leakage. Then we train the logistic regression using gradient descent and NumPy. Then we save the trained model into a JSON file, and then we save metrics like log loss, Brier, ROC, accuracy, and then we generate 4 plots, that is ROC, calibration, coefficient, and one match win probability curve. And finally, a quick what if simulation which tells us the runs remaining -10 and the wicket remaining -1 and minus how does the probability move. So if you don't understand what I'm talking about, just stay with me. I'll be covering everything in this particular video. So let's just quickly go over to my Python file that creates that already stores the backend for the baseline model. And also you guys don't have to worry about the code. I will attach the link to the description for this particular code base. So you can just refer to that and you'll be good to go. So on the top of the file, you can see these imports right here, right? So standard stack, we have pandas for loading, we have NumPy for the math, matplotlib for the plots, and JSON for saving the model, and OS for folders. The random seed is important because we shuffle match IDs for the train test split, and with a fixed seed, your split stays consistent and your results are reproducible. So now I go down to my sigmoid function, my ensure function. So I will explain each and every function to you. Let's start with sigmoid. So I'll just highlight this part and tell you what is this actually talking about. So logistic regression outputs a score that can be anything from -infinity to +infinity. And sigmoid, it turns that score into a clean probability between 0 and 1, right? So now we move on to this function, that is ensure dirs. So I'll just highlight all of this. This is a quality of life thing. It creates the output folders if they don't exist. So we are not deleting anything. We are only ensuring the directories exist. So we are not deleting anything. We are only ensuring the directories exist so saving the file doesn't fail. And as we go down, we have the save clip probs. Now, what exactly is that? Let me highlight this again. So this is a subtle but critical safety fix. So in log loss, we take log probability, and if probability becomes exactly 0 or 1, log 0 would explode. So we clip predictions to a tiny safe range. Now I hope you understand these functions. So we move on to our logistic regression class over here. Now what exactly is this? So this is our model and it has only 2 knobs. You have your learning rate and the number of iterations, and the logistic regression is linear plus sigmoid, and that's it. Now you can see my inside fit function over here. So what we are doing here is we train the model using gradient descent. So first we grab the number of samples, the number of features, and we start weights at 0. That means model, they initially predict 0.5-ish for everything. So as we go down in our code, you spot a linear model of y predicted. So what exactly is that? So this is a core, x dot weights plus bias. It gives a score, and sigmoid, it converts it to a probability. Now as we go down, we see dw and db. Now what is that? This is the gradient. Y predicted minus y is the error signal, and we backprop it into each feature using a dot product. So this is literally the math behind logistic regression training. Now if we go down, you see our update functions over here. So what are we exactly updating over here? So all of this is a log loss, and the lower the log loss is, that's better for us. And every 100 iterations we print it, so you can see training improve. Now, when you go down, you see predict probs. And so what exactly is that? Predict probs and predict. So once trained, predict proba, it returns win probability, and predict uses a zero point 0.5 threshold to convert probability into the win or lose. Now, since you have an understanding about that, and also let me explain you the update. So here what you are actually doing is you update the step. That means you take a small step downhill on the loss. Only after you are done with update, you move on to the log loss. Remember, the lower the log loss, the better it is for us. Then you have your predict probs, and then you have your predict. Now you would move on to your load and pre-process data. So what we are exactly doing here is that we now load the episode to output, that was our match state ball.csv, and we filter it to innings 2 because we are building a chase win predictor, right? So you see features over here, and these are the exact right features from the prompt, and our label is chase win. Now, if the chase was successful, it would be 1, and if the chase wasn't, then it would be 0. And after that, we replace the infinite values and drop NANS. So this matters because at the very end of an innings, RRR can become infinite if overs remaining goes to 0. Now, as we go down, you will see the split train test by match. So what is that? Now this is the part where most people do wrong. We don't split by rows because then the same match appears in both train and test, and the model basically memorizes match patterns. So we split by unique match ID, and entire matches go to either train or test. So as we go down, you see this function over here, right? Now we shuffle the match IDs and then take 20% of the test. So that is what's happening over here. Now, if you go down, you see a function that is normalized features. So this is basically the feature scaling, because runs remaining might be 150 and pressure might be 2, or last 12 wickets might be 1. But if we don't normalize, the gradient descent would become very unstable. And then after that, you go down and you can see this NP mean, NP dot standard over here. So what exactly is that? So here you are calculating the mean and the standard deviation from the training set only, and then we apply the same scaling to test, and that is very critical. So when you go down, you will see a different function, that is evaluate model. So what exactly is that? Here we evaluate 4 metrics. So you have a log loss that punishes confident wrong predictions. Then you have a Brier score that is a mean squared error of probabilities and measures calibration quality. Then you have your accuracy, which is basic classification correctness, and then you have your AUC. Now AUC is the ranking power minus how well the model separate wins versus losses across the thresholds. And ROC close to 1 means the model generally assigns higher probability to winning than the losing states. And ROC close to 1 means the model generally assigns higher probability to winning states than losing states. Now, if you go down, you will see another function that is plot ROC curve. So here what we are doing is we will generate 4 plots. So ROC curve to visualize the AUC. Then you have calibration plot to check if 70% predictions actually win minus 70% of the time. And then you have your coefficient bar chart which features push win probability up or down. And then at last you have one match curve, which is basically how win probability evolves ball by ball in a real chase. And this makes the model explainable and not just accurate. After you go down, you see I have plotted all of my curves. So I have my ROC curve, I have my calibration curve, I have my coefficient curve, and I have my match curve as well. Now, As you go down, you'll see a main function. So what exactly are we doing here is, now we run the pipeline. So we ensure that the folders, they exist, they load the data, they split by match, they normalize features, they train the logistic regression, they evaluate metrics, they save the metrics report, they save the model JSON, they save plots, and and they will also run the what if simulation. So as you can see, I have my load data split by match ID, I have my arrays, I have my normalize, I have my train model, and so on. So after you're done with all of this, we can now just run it. And this Python file, it should print the training loss every 100 iterations and then show the final test metrics and finally a what if simulation. So you just open your terminal and you write Python and your file name. So as you can see, each print is the model getting better, and the loss, it's going down. That means predictions are getting more aligned with the actual outcomes. And if the loss is not decreasing, you usually tune the learning rate or the iterations. So you can also see your metrics getting printed. So you have your log loss, you have your Brier, you have your accuracy, and you have your OC. And I've also generated my plots over here, so and it's all saved within our outputs. So what I'm going to do now is I'm going to my output, then I'll go to my reports and I'll open the episode 3 metrics text that has my log loss, my Brier score, accuracy, and awk. And then I'll go to my models, I'll go to my baseline.json. Then this is the JSON, that is deployable artifact, which it also has like the weights, the bias, the feature names, the normalization mean, and the standard deviation. That means in episode 4, we can just load this and predict win probability for any match state. Now, I will also open my plot, and as you can see, I have a lot of plots generated over here. So first, I will open my ROC curve. So this is my ROC curve, and this ROC curve shows the trade-off between true positives and false positives as we change the threshold. And AUC is the summary number, and closer to 1 is better. So awk of 0.5 means you are guessing randomly. Here our awk is 0.896, then that means that our model is actually pretty good and it's able to predict pretty accurately. Then after that, I'll open my calibration plot over here. So this is the calibration. Now, if the model says 0.8 win probability, does it actually win about 80% of the time? So the closer the curve is to the diagonal, the better calibrated the probabilities are. Now, you go on to your coefficient bar chart. So this is the interpretability, and positive coefficient pushes win probability up and negative pushes it down. And typically, fewer runs remaining and more wickets remaining should help the chase, while higher required run rate and pressure should hurt it. And sometimes, signs look counterintuitive because features are correlated. For example, RRR and pressure overlap with runs remaining and balls remaining. We'll address feature engineering later. And now I'll go on to my one match win probability curve. So this is the most satisfying plot. You have one match ball by ball, and you literally see win probability drop after wickets, jump after boundaries, and stabilize as the chase becomes achievable. And now finally you have your what if test. So now we take a real match state from the test set and then we simulate what happens if we need 10 fewer runs but we also have one fewer wicket. So it's like scoreboard got easier but the batting lineup got weaker, and the model tells us the net effect in win probability. And this is the first step towards the interactive win prediction. You guys might have a lot of questions regarding that. So why are we going for logistic regression? See, I am choosing logistic regression because it's the simplest baseline that outputs probabilities, And before we jump to fancy models, we need a pipeline that we can trust. If a complex model beats this baseline later, we know it's genuinely learning something. And I can also tell you about gradient descent intuition. So gradient descent is just measure error, then it would nudge weight to reduce error, and then it just repeats and iterates. So each feature gets a weight that says how strongly it affects win probability. So that's it for episode 3. Our project is still pending. We'll continue everything in our episode 4, but now I hope you understand that I taught you today, and I'll see you in the next one. Also subscribe to NIIT channel. Thank you.